When we write a chemical equation, we're assuming that all the reactants are used up, but in practice this just doesn't happen. Atoms are so small it's impossible to get exactly the right number to react, so there will always be one reactant where we have some left over. So the amount of product that we can produce is going to be determined by the amount of substance that we have the least of. This is the basis for limiting reagents stoichiometry. For instance, if you wanted to make a bike, you'd need to have wheels, a chain and a frame. In this particular example, the number of bikes we can build here is only 4 because we're limited by the number of wheels that we've got. 8 wheels means that we can only have 4 bikes, even though we've got 5 frames and 5 chains. So in this case, our excess is 1 chain and 1 frame, but we'll have 4 completed bikes. A similar thing happens in chemistry. If we look at this equation, it tells us that 1 molecule of nitrogen combines with 3 molecules of hydrogen to give us 2 molecules of ammonia. But it's unlikely that in a real situation that we would have exactly the right numbers of molecules. So let's consider the situation where before our reaction we actually put in 5 molecules of nitrogen and 9 molecules of hydrogen. Now, if we combine these together to make ammonia, according to our equation, we can only get 6 molecules of ammonia, and that leaves us with 2 molecules of nitrogen left over. So in that case, our nitrogen is going to be our excess reagent, and our limiting reagent, the one that determines how much we're actually going to get, will be our hydrogen. So just to recap those definitions, our limiting reagent is the one which is completely used up. It determines how much product we're actually going to get. Once the limiting reagent is gone, no further reaction can occur, so it will actually stop. The excess reagent is the one that we have more of, that's left over, and that will still remain at the end of the reaction. So to see this in action, let's just consider this reaction, the reaction where we burn sodium in oxygen to give us sodium oxide. From our equation, we can see that 2 moles of sodium combines with 1 mole of oxygen. This is a stoichiometric mixture where everything is used up, there's nothing left over. On the other hand, if we started off with 2 moles of oxygen and 5 moles of sodium, from our equation it tells us the mole ratio that for every oxygen we have, we need 2 sodiums. So if we have 2 moles of oxygen, then we need 4 moles of sodium. We've been given 5 moles, so therefore we're going to have excess sodium left over. So in this case, the limiting reagent is going to be the oxygen because that's the one that's going to be completely consumed. Try another example. If we have half a mole of oxygen, from the equation it tells us that we need twice as much sodium, so we need to have 1 mole of sodium, and we've been given 1 mole, so this again is another stoichiometric mixture where everything's going to be consumed. Another example. Now we've got 1 mole of oxygen and 1 mole of sodium. From our equation, 1 mole of oxygen needs 2 moles of sodium, but we don't have enough sodium. So in actual fact, in this case, the sodium is going to be the limiting factor because it will be used up and the oxygen will be in excess. Can you work out how much oxygen you're going to need to react with 1 mole of sodium? From our equation, we need half as much oxygen as sodium, so therefore only half a mole of the oxygen will react and we'll have half a mole left over. The numbers don't have to be whole numbers, they can be fractions as well. We can work it out in exactly the same way. Our mole ratio is 1:2, so 0.75 of a mole of oxygen needs twice that much sodium, so it needs 1.5. We've been given 3.4, so therefore in this case again we're going to have excess sodium and the oxygen will be our limiting reagent. So to summarise this method, so that you can do it again and again, the first thing we need to be able to do is to recognise when we've got a limiting reagent problem. And the easiest way of doing that is to look and see the information you're given. If you're given quantities of both reactants, then one of them is probably going to be in excess, and that's the way you actually recognise it. Once you've identified the type of problem, then the first thing we have to do is calculate the moles of both of the reagents that we're starting with, or both of the reactants. Then we need to choose one of those values, and by checking with our mole ratio we can calculate how many moles of the other reactant will react with it. It doesn't matter which one you choose, either the first or the second, you'll still get the answer out that you need. Once you've worked out how many moles will react, you compare it with the amount that you've got to see if the second reagent is in excess or whether there's not enough of it, and then you can work out what the limiting factor is. So let's see an actual example. In this problem, we're being asked to find out what the limiting reagent is when the oxygen reacts with the hydrogen to produce water. So obviously the first thing we're going to need is an equation. And with most of these things, we always put the information we know directly underneath it. And in this case, we've got masses given to us. So the 105 goes under the hydrogen and the 1.22 goes under the oxygen. The first step in our procedure, now that we know it's a limiting reagent problem, is to calculate our number of moles. So we just divide our mass by our formula mass, and that will give us our number of moles. So in this case, we've got 0.038 of oxygen and 0.53 of the hydrogen. The second step was to actually take the mole ratio. So we know that 2 moles of hydrogen needs 1 mole of oxygen to react with. So if we took our 0.53 moles of hydrogen, it would need 0.26 moles of oxygen. If we compare that to what we've actually got, we can see that we don't have enough oxygen. We've only got 0.038. So therefore, the oxygen is going to be our limiting reagent because it will be used up completely and we're going to have excess hydrogen left over. So how much hydrogen are we going to have that's left over at the end of this reaction? Remembering that we start with our equation and we calculate the number of moles of each. And we know that oxygen is our limiting factor, so that will tell us how much hydrogen we actually need to react with it. So using our number of moles of oxygen is going to be 0.038, and using our mole ratio, it tells us that we need twice as much hydrogen to react with it. So that will mean that we will consume 0.076 of the hydrogen. But since we know that we have 0.53, the amount of hydrogen that's going to be left over or in excess is just given by the amount we start with, which is the 0.53, minus the amount that actually reacts, which is the 0.076. And the answer is going to turn out to be 0.454 moles left over. So how does finding the excess and knowing what the limiting reagent is help us work out how much product we're going to get? Alright, if we have a look at a situation here, we've got 2 moles of sodium and 1 mole of oxygen, then from our equation it tells us that we should be making 1 mole of sodium oxide. It's a stoichiometric mix. If, on the other hand, we have 2 moles of oxygen and 5 of sodium, we know from our mole ratio that that 1 mole of oxygen gives us 2 of sodium, so therefore 2 moles of oxygen needs 4 moles of sodium. We've been given 5 moles, so therefore the sodium is in excess and our oxygen is the limiting factor. So to work out how much product we are going to produce, we have to start with our limiting reagent. So from the mole ratio, 1 mole of oxygen gives us 1 mole of sodium oxide, so therefore 2 moles of oxygen will give us 2 moles of our product, our sodium oxide. Try another example. In this case, if we have 1 mole of oxygen, the equation tells us that we need 2 moles of sodium, but we don't have enough. We've only got 1 mole. So in this case, our sodium is going to be our limiting reagent. So therefore, we need to look at the mole ratio between the sodium and the sodium oxide. The mole ratio tells us that 2 sodiums gives us 1 sodium oxide, so that means that 1 mole of sodium is going to give us just half a mole of product. But what about if we have masses given to us instead of moles? Can we do the same thing with the equation? Well, not really, because there are going to be different numbers of atoms in different masses. So first of all, we're going to have to convert everything to moles. So summarising our method again, first of all we need our balanced equation and we need to convert all of our masses into moles. Then using our mole ratio we need to determine the number of moles of reactants and hence determine which one is going to be the limiting factor. Once we've got the limiting factor, then we can use that mole ratio to work out how many moles of our product we're going to produce, and then we can convert from our moles back to grams again. So to see how this works, let's start with the example we used before with the hydrogen combining with oxygen. We've already calculated that we had 0.53 moles of hydrogen and 0.038 moles of oxygen. By checking our mole ratio, we know that oxygen is our limiting factor, so we must use our oxygen to work out how much product we're actually going to produce, in this case how much water we're going to produce. So if we look at our mole ratio from the oxygen to the water, we need from 1 mole of oxygen we're going to get 2 moles of water. So if we have 0.038 moles of oxygen, we'll have twice that amount of water in moles. And if we work that out, we get 0.076. But our question has asked us to find out the mass of the water that's produced. So to do that, we need to multiply our number of moles by the molar mass. The molar mass of water is 18, and hence we get 0.076 times 18, which gives us 1.368 grams.